Hello again, and this time we're looking at differential amplifiers. That's a type of amplifier which can amplify up the difference between two signals. Let's have a look at the circuit. It looks like this. Once again, we have the choice of how to analyze the circuit. We could either use superposition, which is okay if we have a linear circuit, or we can do it directly by methods like nodal analysis. Well, let's just revise what we mean by linearity again. A circuit is linear if we change all of the inputs by a factor of alpha, then all of the voltages and the currents everywhere in the circuit will increase by a value of alpha as well. Op-amps are linear components in the sense that their output is linearly related to the difference between their two input voltages. So we can include op-amps in our linear networks and they remain linear. And for a linear network, we can use superposition. And superposition is probably the easiest way to analyze differential amplifiers. So we'll start here. Note that I've set the second voltage source that was here to 0. In other words, replaced it with a wire. What would the voltmeter read in this case? Well, all of that network connected to the non-inverting input really doesn't make any difference at all. There is no current flowing into the non-inverting input, so these two resistors just have 0 volts on both ends. No current is going to flow, no voltage difference will occur across them, which means that the non-inverting input there is just going to be at 0 volts. So I've got this. That is an inverting amplifier. We've seen those before. The output there would just be equal to minus 30k divided by 10k times 1 volt. In other words, minus 3 volts. Next, let's set this voltage source to 0 and consider the effect on this voltage source on the output. This is a little bit of a more complicated circuit because we have to first consider this network here on the non-inverting input. Well, this is a potential divider. The value at the non-inverting input is going to be, in this case, 2 volts through a 10k resistor here, through a 30k resistor there. So the voltage here at this point in the potential divider will just be 2 times 30k divided by the total resistance, which in this case is 40k. So that just gives us 6 over 4 or 3 over 2 volts. That then goes into this circuit. And we've seen this circuit as well before. That is just a non-inverting amplifier. The gain of a non-inverting amplifier is 1 plus this resistor divided by this resistor. In this case, that's a 30k, this is a 10k. So the effect on the output voltage here would be 1 plus 30 over 10, which is just 3, times the input voltage, which is 3 over 2 volts. That would be 4 times 3 over 2, which is 12 over 2, or plus 6 volts. So those are our two contributions to the output voltage, which means that the total output voltage, when both of these inputs were present at the same time, should be the sum of these two contributions to the output, or 3 volts. We can generalize this for any values of resistors or input voltages. For example, this generalized version of the circuit here. Now, if we just consider the effect of A on the output, then we can assume that all of these components here don't make any difference to the non-inverting input. The non-inverting input is just connected to ground, and the effect on A on the output would just be A times Q over P times -1, because this would behave like an inverting amplifier. The input is going into the inverting input of the op-amp. That's our first contribution to the output. I'll call it Vout1. Our second contribution to the output voltage is when B has its value of B and we set A to 0. And in this case, we're getting a potential divider followed by a non-inverting amplifier. The voltage on the non-inverting input there would be B times S over R plus S, the potential divider formula again, multiplied by the gain of the non-inverting amplifier, which is 1 plus Q over P. And that's my second contribution to the output voltage, which I'll call Vout2. So the total output voltage of this circuit would be B times S over R plus S times 1 plus Q over P minus A times Q over P, which is a bit of a mouthful and not particularly easy to work with as a general form. However, if you set S equal to Q and you set P equal to R, so these two resistors were the same value and these two resistors were the same value, then this formula simplifies a lot. It simplifies to this. Q over P would now just be equal to S over R. So we would have B times S over R plus S times 1 plus S over R minus A times S over R, which is BS times R plus S over R minus A times S over R, not forgetting the R plus S down there. Those two cancel. That just gives me B minus A times S over R. In other words, our output is proportional to the difference between our two inputs A and B. And the gain of this differential amplifier is S over R. This resistor divided by this resistor. In fact, to get this result, you don't need to set S equal to Q and P equal to R. All you need is that Q over P is equal to S over R. The ratios have to be the same. And provided we do that, then we have an amplifier here capable of amplifying up the difference between two input signals. This is an incredibly useful circuit for applications ranging from sensors to communications, where you're trying to amplify up the difference between two signals. Once again, we can see it working in the simulator. If both inputs are the same, the output is 0. If this input is above this input, then the circuit here is calculating 3 times this voltage minus this voltage, which is 3 times 0 minus 2, which is 6. The other way round, and it would be calculating 3 times this voltage minus this voltage, which is 3 times 2 minus 0, which is plus 6. If both inputs were set to the same, then the output is 0. And so on. Okay, that's it for this time. Next time, we're looking at a rarer type of summing amplifier, the non-inverting summing amplifier.